Good day students. In the previous class we have seen about the need for sampling. So today we will be continuing with sampling theorem. So we have seen in the previous class that any signal, real-time signal, can be sampled at a specific time interval given by t, or the sampling frequency given by fs is equal to 1 by t. However, the choice of the sampling interval t is very important in performing sampling. So in order to understand what is sampling theorem, let us look into the procedure of how sampling is being done. So we can see here that the real-time signal x of t is given to a sampler which accepts another input del t of t. This del t of t is nothing but a train of impulses, or it can be called by an impulse train. You can observe that all these impulses are equally spaced by a time interval called as t. So this time t is called as sampling time interval, and the corresponding frequency fs is equal to 1 by t is called the sampling frequencies. This sampler can be assumed to be a multiplier, so which multiplies the input signal x of t, which we have taken here as a sine wave, along with the train of impulses del t of t. The corresponding output that we obtain is given by x cap of t. It is very important here that when we study sampling theorem, we need to represent a particular signal both in time domain as well as the frequency domain, or in the spectrum representation is also needed, because only from the spectral representation we will be seeing about the effects of sampling later. So here this figure shows x of t, which is the input signal in time domain, along with its corresponding Fourier spectrum x of omega. So the spectrum of x of omega for this sinusoidal signal is given by a spectrum like this, which can be obtained by applying Fourier transform for the corresponding signal. So we can see here that this spectrum consists of a base band of B, right? So the frequency here is 0 to B. So the fundamental frequency here is 0 to B. In terms of omega, it can be told as 2 pi B, or in turn we can tell that the bandwidth of the given signal is said to be B hertz, or we can tell that this incoming signal frequency has a frequency of B hertz, and in radians it is denoted by 2 pi B. So when this input signal is multiplied by this train of impulse, we get a corresponding x cap of t. Then this sampled signal x cap of t, which is nothing but x of nt. X cap of t can also be represented as x of nt. It is then passed through an ideal low pass filter with a cutoff frequency of B hertz, so that the sampled signal can be reconstructed back into the original signal x of t. So let us see this process of sampling in detail. So initially we have considered here the first phase of sampling. The first phase of sampling, where the input signal x of t and the train of impulses is processed by a sampler to give x cap of t, or this x cap of t can also be represented as our discrete time signal x of n, or in terms of its discrete time samples at every instant, it can also be represented as x of nt. So this input sine signal x of t gets multiplied with this discrete time signal to obtain x cap of t. A careful observation of multiplication of these will give a resultant signal x cap of t, where the actual signal x of t is sampled by samples which are placed at an interval given by this sampling interval t. when we try to plot the corresponding Fourier spectrum of the sampled signal, we get a Fourier spectrum like this. We all know very well that Fourier spectrum is a repetitive spectrum. So for x of t, this is the corresponding Fourier spectrum, and for x cap of t, this will be the corresponding Fourier spectrum. We will prove this in the proof for sampling theorem, how we obtain a frequency spectrum which is repetitive in nature. So as for now, we can just assume that the sampled signal x cap of t in time domain can be represented in frequency domain by its spectrum x cap of omega, which consists of repetitive spectrums. However, our aim is to obtain only, after this sampling step, finally the signal after reprocessing has to be reconstructed back into its original signal. So during reconstruction, we are not bothered about these high frequency components. We need only this frequency component so that we can recover back the original signal. So an observation here shows that the second process where the signal has to be reconstructed. So the sampled signal x cap of t or the discrete time signal x of nt can be allowed to pass through an ideal low pass filter which has a cutoff frequency of b hertz. So when it is passed through a cutoff frequency of b hertz, we can see that the baseband sampling, so the fundamental frequency over here is b hertz or 2 pi b radians. So automatically a low pass filter will obtain only this part of this spectrum and will produce or reconstruct a signal x of omega from x cap of omega. Or we can also tell that x of t, so x of omega is a Fourier spectrum and its corresponding time domain is nothing but x of t. So x of t is successfully reconstructed from x cap of t. So understanding the process of sampling theorem, we will now be able to define what is called as sampling theorem. A signal whose spectrum is band limited to b hertz. The meaning, we can see that the signal that we have taken here has a frequency of b hertz, or we can tell that the bandwidth of the spectrum is b hertz, which can also be told as x of omega equal to 0 for modulus of omega greater than 2 pi b. So we can see here again that this is the value of omega. So for omega greater than 2 pi b and again here lesser than minus 2 pi b, x of omega is 0. Only from minus 2 pi by b to plus 2 pi by b, we have a value of the spectrum. So this is what is illustrated over here. A signal whose spectrum is band limited to b hertz can be reconstructed. Okay, so ultimately after sampling, we need to reconstruct the signal. So this reconstruction is possible without any error from its samples taken uniformly at the rate of fs greater than 2b samples per second. So we mean that the signal that has to be reconstructed can be done without any error only if we choose the sampling frequency fs greater than 2b samples per second. Or in other words, we can say that the minimum sampling frequency is fs is equal to 2b hertz. If we violate this condition, or if we choose fs or the sampling frequency or the sampling time period t, right? That's why we say that the choice of the sampling time period t or the sampling frequency fs is important. In case we choose fs lesser than 2b, we will be seeing in the further videos that we will not be able to reconstruct the original signal after sampling. Hence, sampling theorem states that a signal whose spectrum is band limited to b hertz can be reconstructed exactly without any error only if the sampling frequency is taken at fs greater than 2b samples per second. So in the consecutive video, we will be seeing about the proof of this particular sampling theorem. Thank you.